My name is Ankur Gupta, and I'm starting the project for our course, Machine Learning for Product Management. And in this project, we were given combined cycle power plant data, which uses combination of gas turbines, steam turbines, and heat recovery steam generations to generate power. We have a set of 9,568 hourly average ambient environment readings from sensors at the power plant, which we will use in our model. The columns in the data consist of hourly average ambient variables, temperature, ambient pressure, relative humidity, exhaust, vacuum, net hourly electric energy output, which is our target variable PE. So we are required to use the different models and test them. So what we have taken, the approach is we have used 60% data for training and 20% data for validation and final 20% for test. We tried with two different algorithms here. One was linear regression and another was polynomial regression. Now we go to the implementation. When we use the linear regression or multiple linear regression in this case, as we have various variables, our predicted value or the model came out to be this. We used the linest in order to get the coefficients, a function of Excel, and with those coefficients, we created the model. And then we use the validation test or validation data in order to calculate the predicted PE values. What we saw that between predicted values and actual values, the MAE or mean actual error was average was 3.69 and mean actual percentage error was 0.81%. We also saw root mean square error was 4.6. So if we look into the model stability or the ratio, it was between 1.2 to 1.5, which was 1.25, which is a division of when we divide RMSA to MAE. So it's a good model. But then we also tried with polynomial regression, and there we calculated the polynomial regression using the temperature as square. Everything else remains the same, and then a predictive model came out to be this based upon these coefficients, for which also we use the same function linest. We use the same validation data and calculated the predicted value, and the predicted value and also calculated the mean absolute error, I mean absolute percentage error, and root mean square error. And as you can see in the values here, MAE is 4.63, MAP is 1.02%, and RMSE is 5.9. And the model stability came out to be 1.2, which is also good, but not as good as linear. So we did a graph between linear regression and polynomial regression. And as you can see that the linear regression was 20% better when it comes to MAP, when it comes to MAE, also 20% better, and approximately 22% better when it comes to RMSE. So our statistical deduction was that the multiple linear regression model is most efficient for this data set. There is a high accuracy as MAP is less than 1% and confirms a strong linear relationship between the independent variables TB, AP, RH, and the target PE values. The polynomial regression was rejected due to overfitting, as evidenced by the increase in all error metrics MAE, MP, PE, and RMSE when model complexity was increased. You can also see this from the graph. The orange one is the polynomial regression and the blue one is the linear regression. So these are approximately same values up to a certain point. And then after 470, when it increases, the graph is shifted towards downward, and the blue, which is the linear regression, is upwards. So we selected linear regression as a better model. And we did the test data, we use the test data to run the linear regression, multiple linear regression model. And as you can see, after doing the predictive values according to that model, what came out as MAE and MAPE averages was 2.7 and 0.63%. So, in the final model validation and conclusion, we say the finalized multiple linear regression model was validated using the dedicated test dataset to evaluate its predictive performance on unseen data. The validation yield the following error matrices. Mean absolute error was 2.7 and mean absolute percentage error was 0.63%. The transition from training phase to testing phase showed a significant improvement in our model accuracy. The MAE dropped from 3.69 to 2.7 and MAPE improved from 0.81% to 0.63%. This indicates that the model is not only stable but performs exceptionally well on the new data with an average error of less than 1%. The fact that MAPE is below 1% classified this model as high accuracy by industry standards. Furthermore, the decrease in the error during testing suggests that the linear coefficients are robust and effectively capture the physical relationship between the input variables and the target output PE. The final conclusion is that based upon the comparative analysis between linear and polynomial architectures, the multiple linear regression model is confirmed as an optimal solution for this project. It provides superior precision, lower computational complexity, and better generalization than polynomial alternative. The model is deemed fit for deployment for future predictions within the observed variable ranges. And now we conclude our findings. Thank you very much for listening in, and bye bye.